Hey guys, this lesson is all about finding the derivatives for trig functions. We're only going to focus today on sine and cosine, and we'll look at other trig function derivatives later in the next lesson. But to start, to figure out kind of looking at these trig functions, we're going to do it graphically. To see if we can come up with what these derivatives should be. Now, one thing that you need for this lesson too eventually is you'll need a calculator, so make sure you have that handy because we're going to do some approximations later. And then also you should have in the back of your mind all of the rules that we've already come up with. We've talked about the product rule, we've talked about the power rule, we've talked about the quotient rule. So all those things might be applied with trig functions as well. So let's start out with sine. So we're going to find and look at the derivative of our function sine x, and I'm going to do that again, like I said, I'm going to look at that graphically. So just a quick sketch of what sine should look like. That's kind of woppy, but you get the picture. So if I'm looking at, say, this function sine, I know that there's a relationship between our functions and our function's derivatives, or I can at least look at, consider what a derivative is graphically and use that to maybe even sketch a graph of what the derivative should be. So that's what I'm going to do here, is I'm going to look at this function sine, and I'm going to use that to come up with what my derivative of sine should be. Okay, a while back we talked about important features of graphs, and one of those important features were maximums and minimums. And the key to those important features of maximums and minimums was that my derivative at that point is 0. So at pi over 2, because that's where sine reaches a maximum, at pi over 2 I have a derivative of 0, and at 3 pi over 2, I have a derivative of 0 for my derivative function. So that means that at these places, at pi over 2, I can plot that point. And again, at 3 pi over 2, I can plot a point of 0. So this is telling me what my derivative is based on what my function actually looks like. And likewise, at negative pi over 2, I can plot a point at 0, and at 3 pi over 2, I can plot a point at 0. And so again, what I'm looking for here, what I'm seeing is my zeros appearing, or my maxes and mins appearing on my original graph appear as zeros or roots on my derivative graph. Okay, so at this point, the other thing that we can kind of look at is, like, say at this point here at 0 and say at pi, I have particular slopes, and again, slopes are dealing with derivatives. So if I were to draw a tangent line, and I use that tangent line to estimate that slope, and you can kind of do it now if you want to, like you can play around with your calculator and use 0, 0 as a particular point, kind of like how we did on the first lesson day, and then use, say, pi over 4 or pi over 8 or something like that, and come up with the estimation for it. And what you should find, that estimation should be a positive 1. So if I did do and go through the process, I should get that the derivative at 0 actually ends up being positive 1. And likewise here, the derivative at pi here, if I were going to, again, look at a tangent line, that derivative is going down, and if I did use an estimation and use values that are really close to pi, so pi and then maybe pi plus, I don't know, 0.3 or 0.1 or 0.001 or whatever that may be, and use an estimation for a slope, I should end up getting that derivative is negative 1. It wasn't really to scale, that really should be over there. So I get this function here that, not surprisingly, is a periodic function, and we should recognize that function. So this function that we're dealing with actually is cosine of x. So that's our first derivative for today, is that the derivative of sine is cosine. And likewise, if I found the derivative of cosine, I should end up getting some sort of periodic function too, and I'll draw the graph down below. If I did that same process and found the derivative of cosine, I'm going to use this graph that we have above. I have zeros at 0, I have a 0 over here at pi, I have a 0 over here at negative pi. Those again are my maxes and mins of my now original graph, plot as zeros or roots of my derivative graph. So that's what I'm seeing here for my maxes and mins. And again, I can do a nice estimation. So one of my estimations that I'm looking at, a good point might be at pi over 2. And if I did draw my tangent line approximation at pi over 2, I'm going down, meaning a negative slope. And if I did find values that are around that or found an estimation, a good estimate for that one will end up being -1. And likewise over here at positive pi over 2, if I did, again, find points that are around pi over 2 and use my calculator, come up with a slope and an estimation, I should get that I have an estimate of +1. So again, unsurprisingly, I end up getting some periodic function. This periodic function is something that we should recognize. And it's something that involves sine, of course, but it's not actually sine because sine has a value, or that it goes up and then down, and this one goes down and then up. So this is actually negative sine. So every day we're going to add on a little bit, and this is our addition for today, is that we need to know that the derivative of sine is cosine, the derivative of cosine is negative sine. So from there, we're just going to do a combination of examples that deal with sine and cosine in them. So our first example today is a mixture of polynomial pieces and some trig functions. This is nicely just separated all by pluses and minuses, so I don't have to deal with the product rule, I don't have to deal with the quotient rule. All I have to do is take the derivative of all these things individually. So the derivative of x cubed, bring down the 3, reduce the power by 1, should be 3x squared. Derivative of my next term, bring down the 2, I get 16x to the first power. Derivative of 3 sine, just like before, like that 3 doesn't really mean anything, it just tacks along for the ride. So the derivative of sine is cosine, so it should be 3 cosine x. Again, that -2 doesn't really matter, it's going to tack along for the ride. So the derivative of cosine is negative sine, so I have -2 times negative sine x, and then +4. So that'll end up being 3x squared plus 16x plus 3 cosine x plus 2 sine x plus 4 for my final answer there. So again, that one was just using like power rule with our combinations. But like I said, we kind of have to have everything in our back pocket. So let's do something a little bit more complicated. This obviously is dealing with a power rule situation, but not only that, it's dealing with a product rule because I have a product of two functions, x cubed and cosine. So if I use my product rule tells me I need to take the derivative of my first function, so derivative of x cubed is 3x squared, times my second function, cosine x, plus my first function, which is x cubed, times the derivative of my second function, derivative of cosine is negative sine. And again, we could rewrite that kind of nicely, but I'm just going to leave it for now. Let me give you another one. I'm doing this one specifically, even though it's a lot like the last problem, I'm doing this one because since we don't have like a x squared or x cubed term, a lot of times people forget and they're like, oh, okay, the derivative of x is 1, the derivative of sine is cosine, we're done, it should just be cosine x. But be careful, this is a product of two functions. We do have to use product rule here, even though it's just x and not something like x squared. So derivative of my first function, which is x, will just end up being 1 times my second function, sine x, plus my first function, x, times the derivative of my second function, derivative of sine, is cosine. So we should actually get sine x plus x cosine x, very different than if we took the derivative of these two things and just left it at that. Obviously, that doesn't actually work in this case. So we've dealt with product rule, so let's look at an example with obviously a quotient here. So we're looking at quotient rule involving trig functions. So if you remember, the quotient rule tells us that we need to take the derivative of the top function times the derivative of the bottom function minus the top function times the derivative of the bottom function all over the bottom function squared. So derivative of the top function x is just 1 times my bottom function cosine x minus my top function, which is x, times the derivative of my bottom function, which is negative sine x. Derivative of cosine is negative sine, all over my bottom function cosine x quantity squared. So we should end up getting cosine x, and this will end up being plus x sine x over cosine squared x. Again, you could write this differently. You could cancel out a cosines here, plus x sine of over cosine squared, and sine over cosine will be tangent. So you could write it as like secant plus x tan secant x. That's possible too, just so you know. You should be able to kind of recognize all forms of this. Let's do, again, we're kind of just going to go through bunch of different forms here so that we're comfortable. I'll actually have you do this one, like pause the video and try this one. It's not super different from the last one. So if you did end up doing this one, I'll work through it, but you can kind of skip to the end if you want. If we take the derivative, again, quotient rule, take the derivative of the top function, that 1 will become a 0. The derivative of cosine is negative sine, but this is negative cosine, so negative negative sine will be positive sine x times the bottom function, x squared, minus the top function, 1 minus cosine x, times the derivative of the bottom function, which will be x squared. Or sorry, will be 2x. I said x squared, but wrote 2x, wrote the actual answer. And that's all over the bottom function, x squared, quantity squared. So some simplification. In the numerator here, I'll get x squared sine x. I'm going to end up having to distribute the 2x and distribute this negative 1. So 2x times negative 1 will be negative 2x. 2x times negative 1 times negative cosine x will be positive 2x cosine x. All over x squared squared, which is x to the 4th. And because each of these terms does contain an x, you could simplify this a little bit further by taking out an x on every one of the terms. So if you do that, you'd end up having x sine x minus 2 plus 2 cosine x, all over x cubed. So, simplification of that last one. Right. One more, just generic, plugging in, applying these rules. So our last function that we're going to deal with is sine x cosine x all over x cubed. Alright, this one's a little bit more complicated yet because we're dealing with not only a quotient, obviously, but we're also dealing with a product. So this is a product rule within the quotient rule. So when we take the derivative of that top function, it's a little bit, like we have to apply the product rule, so it'll be a little bit longer, a little bit more complicated. If I was doing the product rule here for the derivative of the top function, I would have to take the derivative of my first function, which is sine x. So the derivative of sine is cosine. So I'd have cosine x times our second function, which is cosine x, plus sine x, times, that's our first function, times derivative of our second function. Derivative of cosine is negative sine. That's the derivative of the top so far, times the denominator, x cubed, minus the top function sine x, cosine x, times derivative of my bottom function here. So I'd bring down the 3, reduce power by 1. I'd get 3x squared all over x cubed quantity squared. There's definitely some simplification that can be done. Obviously, we'd end up getting cosine squared minus sine squared. That doesn't combine to 1, so be careful. It's not the Pythagorean identity. And then you could cancel out some of these x's from the top and bottom to get your final answer. So if you do that, and again, I would recommend that you pause and you do that simplification so you can make sure that you're getting everything correct. You should end up getting x times cosine x squared minus sine x squared, or sorry, cosine squared x minus sine squared x minus 3 sine x cosine x. And you could write this differently, of course, over x to the fourth. Like you could distribute that x and you could write it in different ways and factor it out differently, but that's what you should get here at the end. Okay, the last part of today is going to be going back to our favorite thing, which is tangent lines. I told you a few lessons ago that we almost always use tangent lines in every chapter. I don't think there's a chapter or unit that we don't use a tangent line. So we need to get good at it, and to kind of work on that today, we're going to be dealing with a function that deals with sine of x over x. And we're going to be using our tangent lines to come up with an approximation. So the reason that we have tangent lines, honestly, is because linear functions are way easier to work with than curves. If I'm looking at some, linear thing, and I'm dealing with a curve, it's a lot easier to use that linear function to extrapolate and get an approximation that's close to that particular point than actually, like, say, evaluating this function. So if I wanted to find, y of, I don't know, 0.1 or something like that, it's really annoying to do that by hand. It's really annoying to actually find an actual value, but maybe if I found the tangent line at 0, and again, this is not actually sine x, or this is not this function, but like let's pretend that we're dealing with this curve. If I found it at 0 and I use the tangent line, I could use that tangent line to get a really good approximation for something that's slightly more than that. So that's the idea here, is that tangent lines are really helpful because it's a linear representation of what that curve is, or what's happening with that curve at that moment, and linear functions are just so much easier to deal with than curves. So our first problem for this is to find y prime. So we've been doing this already. This is a quotient, obviously, so to find y prime, or f prime of x, I would end up using the quotient rule, which derivative of sine here is cosine, times our bottom function, which is x, minus our top function, sine, times the derivative of our bottom function, derivative of x is just 1, all over our bottom function squared. So this simplifies to x cosine x minus sine x over x squared. My next question to do is write the equation of the tangent line at x equals pi over 2. So again, we've done tangent lines before. We've said that tangent line is, again, just a line. It's looking at a linear representation. You need two things to write the equation of a line. We need a point, and we need the slope at that particular point. So I know that I'm dealing with x equals pi over 2. I don't have a point per se yet. I just have an x value. So I need to find the corresponding y value, and I can use my original function to do that. So if I find y of pi over 2, and I evaluate into my function, sine of pi over 2 is just 1, and then my x value here would be pi over 2. So if I rewrite that, multiply by the reciprocal, I should get 2 over pi here for my y value. So now I am dealing with the corresponding, or the coordinate point, pi over 2, comma, 2 over pi. And also I need a slope at that point, and slope in calculus means derivative. So I came up with the derivative. That means that I can find the slope at that particular point. Okay, so I have pi over 2 times cosine of pi over 2. Well, cosine of pi over 2 is just 0, so that'll end up being 0 for my first term, minus 1 all over pi over 2 quantities squared. So I get negative 1 over pi squared over 4. So to make that easier, I'm going to multiply by the reciprocal. I should get negative 4 over pi squared. So my tangent line, I always write in point slope form. So my y value is 2 over pi, so y minus 2 over pi equals my slope, negative 4 over pi squared, times x minus pi over 2. Remember, tangent lines use the same slope. If I asked you to find the normal line, you would do opposite and reciprocal for that, so just be careful. And my last question for you is to use the tangent line to estimate y of 1.6. Now we're using our tangent line to estimate the value y of 1.6 because pi over 2, which is the equation that we wrote our tangent line around, that particular point, that point is pi over 2 is about 1.57, so 1.6 is really close to that, which means that our tangent line might be a really good estimate. It's something that's really close to it. So 1.6 is pretty close. We kind of centered it around this value. All this is really saying to us is take this linear function that we dealt with, which is obviously a little bit tricky, it's a little bit ugly, but it's saying evaluate this function, find y when x is 1.6. Okay, so this is where you need your calculator. So in your calculator, estimate this value. When you do that, you should end up with about 0.24 or 6247, blah, blah, blah. In calculus and an AP test, you always, if you have a decimal approximation, you always want to round to 3 decimals. So our answer then rounded to 3 decimals would be about 0.625. We could obviously leave it as an exact answer too, but this is something that we would have a decimal approximation, and it should be about 0.625. Now we can actually see if we take our calculator and again, calculus always run to 3 decimal places in an AP test, but also calculus always deals with radians. So make sure that if you were going to actually use or graph or anything like that, make sure that you're in radian mode. I could find out how good of an approximation this is. So if I actually go back up to my original function, which was sine x over x, I could find the actual exact value of that, and it's pretty darn close to what we ended up getting. So we're off by a little, obviously. It was 0.62478, I think. But we're off by, like, you know, super small amount. The error here is super tiny, and it doesn't always happen with every tangent line. But this, again, is like a really good approximation for a value that's really close to the one that we centered around. That's also a really common question, is just dealing with tangent line approximations, so that's something to get comfortable with as well.